Hello there, and welcome to Mr. Sleepy Science. Tonight, we're going to drift into the unknown, into the questions that science hasn't solved yet. For all the discoveries we've made, the universe is still packed with puzzles, mysteries, and things nobody can fully understand. Some are cosmic, reaching across galaxies and black holes. Others are right here on Earth, in the oceans, the sky, and even inside our own bodies. These open questions remind us that science isn't a book of final answers, but an endless story that's still being told. Every mystery opens a door to wonder, reminding us that we're explorers in a universe far bigger than we can yet imagine. If you enjoyed drifting off to scientific wonders, feel free to like and subscribe, or simply drop your thoughts in the comments. It helps others find their way here too. But for now, let these questions carry you. And if you're ready, let's begin. We still don't know why the universe exists at all. It seems like the most basic question you could ask. Why is there something instead of nothing? And yet, science has no answer. Physics can explain how the universe behaves once it exists. Cosmology can trace things back to the Big Bang. But why there is a universe at all, why there are laws that allow it to be here, stays unsolved. Quantum physics tells us that what we call nothing isn't truly empty. Even the vacuum of space is buzzing with activity, tiny particles that flicker into existence before vanishing again. Some scientists think the universe itself might have appeared in the same way, that absolute nothingness is unstable, and something must always come into being. Others suggest that maybe our universe is just one of countless universes in a vast multiverse, each one popping into being with its own laws. But if that's true, it only leads us to a deeper question. Why should the multiverse itself exist? Philosophers sometimes say that existence is simply the natural state, that non-existence is impossible. Maybe reality, in some form, must always be. But these are ideas we can't test. No telescope, no particle collider can measure why there is being instead of nothing. Every other question in science rests on this one. Every star in the sky, every atom in your body, every law of nature, all exist on a foundation we cannot explain. The fact that reality is here at all stays the deepest mystery we face. The spark that set the cosmos in motion is still a mystery. We can trace the universe's story back nearly 14 billion years to a time when it was a hot, dense fireball. We call this beginning the Big Bang. But what actually caused it? That stays unknown. Cosmologists have put together a detailed history from the moment the universe was only fractions of a second old. In that first instant, rapid expansion called inflation may have blown space itself wide open. But what triggered inflation? Why did it start? And why did it end? These questions stay unanswered. Some theories imagine the Big Bang as a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time themselves. Others suggest that the Big Bang wasn't the first event, but only one moment in a cycle of births and deaths, with universes expanding, collapsing, and beginning again. What complicates the question further is time itself. If the universe includes the birth of time, then asking what came before may not even make sense. Our instruments, the Hubble Space Telescope, the Planck satellite, and the new James Webb give us snapshots of the infant universe, but none can peer into the first instant itself. We know the universe began. We can measure its age, chart its growth, and study its afterglow. But the spark that set the cosmos in motion, the true first cause, is a mystery still hidden in the dark. Time always flows forward, but no one can explain why. Every moment, the present slips into the past. We remember yesterday, but not tomorrow. A broken glass never leaps back together. Heat moves from hot coffee into the air, but never the reverse. Time in our experience only flows one way. This is called the arrow of time. What makes it strange is that the basic laws of physics don't require this. At the smallest scales, particles can move forward or backward in time with equal ease. The equations are symmetrical. Nothing in them demands that time should only advance. And yet, our entire world depends on this one-way street. Scientists often connect the arrow of time to entropy, the tendency for disorder to increase. The universe began in a very ordered state and has been running down ever since. But why did it begin that way? Why should the cosmos have started in such a low entropy condition that time could even have a direction? Some physicists think the arrow of time might come from the way information spreads. Others suggest it is tied to the expansion of the universe itself. But none of these explanations are complete. Time's direction is something we live inside of every second of our lives. And yet why it flows forward, and only forward, stays one of the most haunting mysteries of science. Most of the universe is made of something we cannot see. When galaxy stars measure the way galaxies spin, they find something strange. Stars near the edges move far too quickly, as if held by an invisible force. By all logic, those stars should drift away into space. Instead, they remain bound. The conclusion is hard to escape. Most of the mass in the universe is not visible to us. We call it dark matter. Dark matter neither glows nor absorbs light. Telescopes cannot see it directly. Yet we know it must be there because its gravity shapes everything around it. It holds galaxies together, bends the paths of starlight from distant clusters, and leaves faint ripples in the pattern of the cosmic web.
So what is it? Scientists have searched for decades. Some think it is made of undiscovered particles, perhaps WIMPs, or weakly interacting massive particles. Others suggest axions, ghostly particles that barely interact with ordinary matter. There are even theories that dark matter could be black holes formed in the earliest moments after the Big Bang. Despite enormous effort, we still don't know. Experiments buried deep underground wait for a passing dark matter particle to collide with a single atom. So far, none have. For now, this hidden mass, 5 times more abundant than ordinary matter, stays one of the universe's greatest unsolved mysteries. An invisible force is stretching space apart faster and faster. In the 1990s, astronomers studying distant supernovae expected to see the universe's expansion slowing down. After all, gravity should be pulling galaxies back together. Instead, they discovered the opposite. The universe is not just expanding, it is accelerating. This means some unknown energy is embedded in space itself, pushing galaxies away from each other at ever-increasing speeds. We call it dark energy, though the name is only a placeholder for our ignorance. Dark energy makes up nearly 70% of the entire cosmos, yet we don't know what it is. One idea is that it is a property of the vacuum, a kind of constant energy present in empty space. Another possibility is that it points to new physics, perhaps a dynamic field that changes over time. Some theories even suggest it could be a sign that our understanding of gravity itself is incomplete. What makes the mystery even more unsettling is its consequence. The universe's fate depends on this invisible force. If dark energy remains constant, galaxies will drift farther apart until only empty space is left. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms. We can measure its effects, but we cannot see its true nature. Dark energy is the unseen hand shaping the ultimate future of the universe. The laws of physics seem tuned for life in ways we don't understand. The universe appears balanced on a knife's edge. If gravity was slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form. If the electromagnetic force were different by a fraction, atoms would not bind together. Even the tiniest changes in the constants of physics could erase the possibility of life altogether. This puzzle is known as the fine-tuning problem. Why should the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or nuclear forces to take the strengths they have. And yet, if they were different by even a little, our universe would be lifeless. Some argue this is coincidence. Others suggest that countless universes exist, each with different laws, and we simply live in the rare one where life is possible, a cosmic lottery win. Another idea is that there may be a deeper principle, still undiscovered, that forces the laws to take these exact values. For now, we cannot say. But when we look around at stars, planets, and the fact that we can even ask this question, we are reminded that the universe feels improbably, strangely suited for life. And why that is so stays one of science's greatest mysteries. No one knows if the universe goes on forever or ends somewhere. The observable universe is vast, about 90 billion light-years across, but we cannot see beyond it. Light has only had so much time to travel since the Big Bang, and so there is a horizon we cannot look past. But what lies beyond that edge? One possibility is that the universe is infinite, stretching endlessly in all directions with no boundary at all. If so, then space may contain an unending number of galaxies, stars, and perhaps even other Earth-like worlds. Another possibility is that the universe is finite but unbounded, like the surface of a sphere. In such a universe, if you could travel far enough in one direction, you might eventually return to your starting point. Scientists search for answers in the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns might reveal the universe's shape. So far, the evidence suggests that the universe is very nearly flat, but this does not settle the question of whether it is infinite. For now, we don't know if the cosmos stretches without end, or if it loops back on itself. The true size and shape of the universe stay hidden, just beyond our reach. Beyond the horizon of what we can see, there may be endless unknowns. When we look into space, we are also looking into the past. The most distant galaxies we can see are sending us light that has traveled for over 13 billion years. But beyond that lies a region forever hidden, the unobservable universe. This cosmic horizon is not like a physical wall. It is a limit set by the age of the universe and the speed of light. Beyond it, reality continues, but we can never know exactly what is there. Perhaps it is much the same. galaxies, stars, and planets stretching far beyond our sight. Or perhaps it is very different, with regions governed by different conditions or even different physical laws. Some theories of inflation, the rapid expansion thought to have occurred right after the Big Bang, suggest that our observable patch is just one bubble in a much larger reality. If true, the vast majority of the universe lies forever beyond what we can measure. We are bound within a cosmic island. The sky we see is only the smallest fraction of what may exist. The rest of the universe is out there, silent and unreachable, a permanent unknown. Some scientists believe there are other universes, but we cannot prove it. The idea of the multiverse is one of the boldest in modern science. It suggests that our universe may not be unique, but one of countless others. Each universe could have different laws of physics, different histories, even different numbers of dimensions. The concept comes up naturally in some theories. Inflation may create bubble universes, each budding off with its own conditions. String theory predicts a vast landscape of possible realities. In such scenarios, our universe is simply one outcome among many. This could even explain fine-tuning. We live in a universe suited for life because only in such universes can observers exist. But there is a problem. If other universes exist beyond our cosmic horizon, we may never be able to observe them. No light or signal could ever cross the boundary. This makes the multiverse both fascinating and controversial. It stretches the definition of science because an idea we cannot test may never be more than speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most interesting mysteries in physics. Space and time may be woven from deeper rules we haven't discovered. Ancient Einstein's general relativity shows us that space and time are not fixed backdrops, but flexible and dynamic. They bend, curve, and stretch, shaping the paths of planets and the flow of light. But what, at the deepest level, is this fabric made of? At the smallest scales, relativity and quantum mechanics clash. Space and time seem smooth in relativity, but quantum theory suggests that everything should be grainy, fluctuating, and uncertain. Bringing these two views together is one of the greatest challenges in science. Some ideas suggest that space and time are not fundamental at all. Instead, they may come from something deeper, perhaps a network of quantum information or entanglement patterns that give rise to geometry. In this picture, what we call space-time is like a surface, and underneath lies a more basic reality we cannot yet see. Some wonder if time itself is even real, or if it is an illusion created by deeper processes. If so, our basic sense about reality would be wrong. Space and time feel like the stage on which the universe unfolds. Yet the stage itself may not be what it seems. What they truly are stays one of the deep unanswered questions in science.
Gravity is the weakest force, and no one knows why. Of all the fundamental forces in nature, gravity is by far the weakest. An ordinary refrigerator magnet can overcome the gravitational pull of the entire Earth. A tiny amount of electromagnetic force lifts a paperclip against the weight of a planet. This imbalance is puzzling. Gravity works across vast distances and holds galaxies together, but at the atomic scale, it is so weak that physicists often ignore it. Why should gravity be so much weaker than electromagnetism or the nuclear forces? There is no clear answer. One idea is that gravity may be leaking into extra dimensions we cannot see. In theories with higher dimensional space, gravity could be strong elsewhere, but appear diluted in our three-dimensional world. Another possibility is that gravity operates differently at very small scales in ways we have not yet understood. The weakness of gravity also connects to the fine-tuning problem. If it were much stronger, stars would burn out quickly and life might never have time to evolve. If it were weaker, galaxies might not form at all. For now, gravity remains the odd one out.
Why it is so feeble compared to the other forces stays a mystery that hints at deeper physics still waiting to be discovered. We don't know if gravity works the same way everywhere in the universe. Einstein's general relativity has passed every test we've thrown at it. It explains how planets orbit, how light bends around stars, and even predicts black holes and gravitational waves. But does gravity behave the same way in every corner of the cosmos? We cannot be sure. On Earth and in our solar system, gravity acts exactly as predicted. But at the largest scales, something seems off. Galaxies spin too fast. Galaxy clusters hold together more tightly than they should. This has led to the idea of dark matter. But what if instead, gravity itself behaves differently on cosmic scales? Some scientists have proposed modified gravity theories. These suggest that at very large distances, gravity might deviate from Einstein's equations. If true, we might not need dark matter or dark energy at all. But so far, these ideas struggle to match all the data. On the other extreme, at the smallest scales, near black holes or at the moment of the Big Bang, gravity might break down completely. We cannot yet test this because we lack a full theory of quantum gravity. So, while gravity seems universal, we only know it works where we can measure it. Beyond that, it may surprise us. Whether gravity is truly the same everywhere or changes in ways we haven't detected stays an open question. Quantum mechanics says particles exist in many states at once, but why does reality pick just one? In the quantum world, particles do not have fixed positions or properties until they are measured. Instead, they exist in a kind of blur called a superposition, occupying many states at the same time. But the moment you look, the blur collapses and reality settles on a single outcome. This is the measurement problem, and it is one of the deepest puzzles in physics. Why does observation cause the collapse? What counts as a measurement? Is it a conscious observer, or does any interaction work? Some physicists think that the wave function, the mathematical description of a particle's possible states, is not a real thing, but just a tool for prediction. Others believe it is real, and that collapse is a physical process we do not yet understand. The many worlds interpretation offers a radical alternative. It suggests that the wave function never collapses. Instead, every possible outcome happens, each in its own branching universe. When you measure a particle, the universe splits, and every version of you sees a different result. Despite a century of experiments, no one knows which interpretation is correct. Quantum mechanics works perfectly for making predictions, but what it means about the nature of reality stays one of the most haunting mysteries in science. We cannot combine quantum mechanics and gravity into one theory. Physics rests on two pillars. Quantum mechanics governs the very small, atoms, particles, and forces at tiny scales. General relativity governs the very large, stars, black holes, and the shape of space-time itself. Both theories are incredibly successful, but they do not fit together. The problem shows up most sharply inside black holes and at the birth of the universe. These are places where the very small and the very large collide. Relativity says space-time is smooth. Quantum mechanics says everything should be grainy and uncertain. When you try to apply both at once, the math breaks down. For decades, physicists have worked on a theory of quantum gravity, something that could unite the two. String theory is one attempt, suggesting that particles are not points, but tiny vibrating strings. Loop quantum gravity is another, imagining space-time itself is woven from quantum loops. But none of these ideas have been proven. We lack the technology to test them. The energies needed are far beyond anything we can create in a lab. Until we find a way to merge quantum mechanics and gravity, our understanding of the universe stays incomplete. This missing piece is one of the greatest challenges in all of science. Inside a black hole, the laws of physics may break down completely. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. At its center lies the singularity, a point where matter is crushed to infinity and space-time curves without limit. But what actually happens there? No one knows. General relativity predicts the singularity, but it also breaks down at that point. The equations give infinite answers, a sign that something is missing from our understanding. Quantum mechanics should become important in such extreme conditions, but we do not yet have a theory that can handle both gravity and quantum effects together.
Some physicists think the singularity is not real, but a placeholder for physics we do not understand yet. Perhaps at the core of a black hole, space-time becomes something else entirely, a quantum foam, or a region where time and space lose their usual meaning. Others wonder if information is destroyed inside a black hole, violating one of the basic rules of quantum mechanics. Or maybe information somehow escapes, encoded in the event horizon in ways we are only beginning to explore. We cannot see inside a black hole. The event horizon blocks all light, so what happens at the singularity may remain forever hidden. It is a place where the known laws of physics cannot reach, a boundary between the universe we understand and the one we do not. We don't know if information can escape a black hole or is lost forever. When something falls into a black hole, it seems to vanish. But according to quantum mechanics, information about the physical state of particles cannot simply disappear. This creates a paradox. Stephen Hawking showed that black holes should slowly evaporate by emitting radiation. Over time, they shrink and eventually disappear completely. But Hawking radiation seems to carry no information about what fell in. If the black hole vanishes, where does the information go? Some physicists believe information is stored on the event horizon, the boundary of the black hole, in a kind of two-dimensional code. This idea comes from the holographic principle, which suggests that all the information in a volume of space can be encoded on its surface. Others think information is released in subtle patterns in the radiation itself, patterns too complex for us to decode yet. Still others wonder if the paradox points to a deeper flaw in our understanding of time, space, or quantum mechanics. For now, the black hole information paradox stays unresolved. It sits at the intersection of gravity, quantum theory, and thermodynamics, hinting that one or more of these frameworks must be revised. What happens to information in a black hole is more than a puzzle, it is a doorway to new physics. We know what happens when the wave function collapses. In quantum mechanics, particles exist in a blur of probabilities until they are observed. Then, suddenly, they snap into a definite state. This moment is called wave function collapse. But what actually causes it? That question has no agreed-upon answer. Some physicists believe collapse is a real physical process, triggered by measurement. But what counts as a measurement? Does it require a conscious observer, or is any interaction enough? No one is sure. Others argue collapse is not real. In the many worlds interpretation, the universe simply branches into different versions, each one reflecting a different outcome. You do not see the collapse. You only see one branch while others continue unseen. There are even theories that suggest collapse happens spontaneously, driven by gravity or some other unknown mechanism. In this view, large objects naturally settle into definite states, which is why we do not see everyday things in superposition. Despite nearly a century of debate, the question stays open. Wave function collapse is central to quantum mechanics, yet we cannot say what it is, why it happens, or even if it is real. This gap in understanding is one of the most fundamental mysteries in physics. We cannot explain why particles have the masses they do. Every particle in the universe has a specific mass. Electrons are light. Protons are heavier. The top quark is the heaviest of all. But why do they have these particular values? Physics has no answer.
The Higgs field is thought to give particles their mass by interacting with them as they move through space. The more strongly a particle interacts with the Higgs field, the more mass it has. But this only shifts the question: why do particles couple to the Higgs field in the way they do? The standard model of particle physics can describe the masses, but it cannot predict them. The values must be measured and plugged into the equations by hand. There are around 20 such free parameters, numbers that seem arbitrary. Some physicists hope that a deeper theory, perhaps one that unifies all the forces, will explain where these masses come from. Others wonder if the values are just accidents, outcomes of the way our universe happened to form. For now, the masses of particles stay one of the unexplained features of nature. They shape everything from the structure of atoms to the fate of stars, yet we don't know why they are what they are. The Higgs field gives particles mass, but we don't know why it exists. In 2012, scientists at the Large Hadron Collider discovered the Higgs boson, a particle that confirmed the existence of the Higgs field. This invisible field fills all of space, and it is what gives particles their mass. Without it, electrons, quarks, and everything else would be massless, and the universe as we know it would not exist.
But discovering the Higgs only answered one question and opened many more. Why does the Higgs field exist at all? Why does it have the strength it does? And why does it give particles the specific masses they have? The Higgs field also has a strange property. Its energy in the vacuum, the state of lowest energy, is much lower than theory predicts. Quantum fluctuations should push it to enormous values, yet somehow it stays small. This is called the hierarchy problem, and it has no solution. Some think new particles or forces we have not discovered yet might stabilize the Higgs. Others suggest that the field's properties are fine-tuned by deeper principles or by the conditions of our universe, among many. The Higgs field is real. We have measured it. But why it exists, why it has the properties it does, and what keeps it stable are mysteries that reach into the very foundation of reality. We don't know if there are more dimensions beyond the ones we see. We live in a world of 3 spatial dimensions: up and down, left and right, forward and back, plus time. But some theories suggest there may be more dimensions, hidden from our senses. String theory, one attempt to unify all forces and particles, requires extra dimensions. Depending on the version, there could be 6, 7, or even more. These dimensions are thought to be curled up so small that we cannot detect them, like the surface of a thread that looks one-dimensional from far away, but has width up close. If extra dimensions exist, they could explain some of the deepest puzzles in physics. They might account for why gravity is so weak, or why particles have the masses they do. They could even provide space for hidden forces or particles we have never seen. But despite decades of theoretical work, we have no direct evidence. Experiments at particle colliders have searched for signs of extra dimensions, but found none so far. That does not mean they are not there, only that if they exist, they are smaller or more hidden than we can currently probe. The question of whether reality has more dimensions than we experience stays open. It is a reminder that the universe may be far stranger than what we can see or touch. Some particles seem to break the mirror symmetry of the universe. In physics, symmetry is a powerful tool. If the laws of nature look the same when you flip left and right or swap particles for antiparticles, that tells us something deep about reality. For a long time, physicists believed the universe obeyed these symmetries perfectly, but experiments have shown otherwise. Certain weak force interactions involving particles called kaons and b-mesons do not respect the symmetry between matter and antimatter. This is called CP violation. The discovery was shocking. It means the universe has a subtle preference, a bias that breaks the mirror. This asymmetry may explain one of the biggest mysteries of all: why the universe is made of matter and not antimatter. In the moments after the Big Bang, matter and antimatter should have been created in equal amounts. They should have annihilated each other, leaving only energy. Yet, here we are. Stars, planets, and life, all built from matter. Antimatter is almost nowhere to be found. This imbalance is called baryon asymmetry, and it is one of the great unsolved mysteries. Scientists know there must have been some process that favored matter over antimatter, even if only by a tiny fraction. Over time, that small difference became everything we see. CP violation, the breaking of certain symmetries in particle physics, offers a clue. But the effects we have measured are not strong enough to explain the full asymmetry. There must be other processes, perhaps involving particles or forces we have not yet discovered. Some theories point to conditions in the first moments of the universe, others to exotic phenomena like leptogenesis, but none are proven. The existence of matter is not a given. It is a mystery, and without solving it, we cannot fully understand why the universe is here at all. No one knows why the universe began with such perfect order. The second law of thermodynamics says that entropy, or disorder, always increases over time. A broken cup does not reassemble itself. Heat flows from hot to cold, never the reverse. This is one of the most reliable patterns in nature. But it raises a troubling question. If entropy always goes up, the universe must have started in a state of incredibly low entropy, almost perfect order. Why? At the moment of the Big Bang, matter and energy were distributed in a very smooth, uniform way. This is the opposite of what we might expect. Random conditions should have led to chaos, not order. Yet the early universe was strangely organized, and that initial order is what allowed stars, galaxies, and eventually life to form. Some physicists think this smoothness came from inflation, a rapid expansion in the first fraction of a second. But inflation itself requires specific starting conditions. So the problem is not fully solved, only pushed back.
Others wonder if the universe is part of a larger cycle where order and disorder trade places over cosmic timescales. Or perhaps the answer lies in the nature of time itself. For now, the low-entropy beginning of the universe is a mystery. It is the reason we have a past and a future, and yet we do not know why it is so. We don't know why the constants of nature have the exact values they do. The universe is governed by a set of numbers: the speed of light, the strength of gravity, the charge of the electron. These are called the fundamental constants, and they define how reality works. But why do they have the values they do? There is no equation that predicts them. They cannot be derived from deeper principles. Instead, they must be measured and written into our theories by hand. What is especially strange is how precise some of these numbers are. If the strength of the strong nuclear force were different by just a few percent, atomic nuclei could not form. If the cosmological constant were much larger, the universe would have torn itself apart before galaxies could grow. This has led some scientists to propose that the constants are not fixed at all. Perhaps they vary across different regions of space or in different universes. In a multiverse, every combination might exist, and we simply live in one where the constants allow life. Others believe there is a hidden principle that forces the constants to take these exact values, something we have not yet uncovered. For now, the constants of nature are like dials, set to very specific positions. We can measure them, but we cannot explain them. And that makes them one of the deepest puzzles in physics. Particles can be connected across any distance in ways that seem impossible. In quantum mechanics, two particles can become entangled. Once entangled, they remain connected no matter how far apart they are. If you measure one, the other responds instantly, even if it is on the other side of the galaxy. Einstein called this spooky action at a distance. He thought it proved quantum mechanics was incomplete, but experiments have confirmed it again and again. Entanglement is real. What makes it so strange is that nothing seems to travel between the particles. No signal, no force, no message. Yet they behave as if they are still one system. Change one, and the other changes too. This does not allow faster-than-light communication. You cannot control what result you get when you measure a particle, but the correlation between entangled particles is perfect, and that is deeply mysterious. Some interpretations suggest that entangled particles share a connection outside of space, woven into the fabric of reality itself. Others think entanglement hints that space and time are not as fundamental as we believe. Entanglement has practical uses. It is the basis for quantum computing and quantum cryptography. But what it means about the nature of reality stays one of the most puzzling and beautiful mysteries in physics. We cannot predict exactly when a radioactive atom will decay. Radioactive decay is one of the most common processes in nature. A uranium atom sits quietly, and then, without warning, it splits apart. We know the odds. We can say that half of a sample will decay in a certain time, the half-life, but we cannot say when any single atom will go. This randomness is not due to ignorance. It is not that we are missing some hidden detail. Quantum mechanics says the decay is truly random, fundamentally unpredictable. This troubles some people. It suggests that the universe, at its core, is not deterministic. Events can happen without a cause, at least not in the way we usually think of cause and effect. Einstein famously rejected this idea, saying, "God does not play dice." But every experiment has supported quantum randomness. Radioactive decay, particle interactions, even the emission of light from atoms, all happen in ways that cannot be predicted exactly, only statistically. Some interpretations of quantum mechanics, like many worlds, offer ways to think about this differently, but none remove the randomness from the equations. The fact that we cannot know when an atom will decay is not a flaw in our tools. It is a feature of reality, and it is a reminder that the universe is stranger than common sense allows. We don't know if the universe will expand forever or collapse back in on itself. The universe has been expanding since the Big Bang. Galaxies are moving apart, and space itself is stretching. But what will happen in the distant future? Will this expansion continue forever, or will it one day reverse? The answer depends on the total density of the universe and the nature of dark energy. If dark energy stays constant, the universe will keep expanding. Galaxies will drift farther apart, stars will burn out, eventually space will be cold, dark, and nearly empty. This is called the heat death, or big freeze. But if dark energy changes over time, the story could be different. If it weakens, gravity might one day win, pulling everything back together in a big crunch. If it grows stronger, it could tear apart galaxies, stars, planets, and even atoms in a big rip. There is also the possibility of a cyclic universe, where expansion and contraction happen over and over, each cycle creating a new cosmos. Right now, measurements suggest the universe will expand forever, but our understanding of dark energy is so limited that we cannot be certain. The ultimate fate of the cosmos, whether it ends in ice, fire, or something entirely different, remains an open question. Some scientists think the universe could suddenly change into a lower energy state and destroy everything. The Higgs field, which gives particles their mass, exists in what is called a vacuum state. But there is a troubling possibility. This state might not be the lowest energy state possible. It could be a false vacuum, stable for now, but not forever. If that is true, then at some point the Higgs field could suddenly drop to a lower energy level. This transition would happen at the speed of light, creating a bubble of new physics that would expand outward, rewriting the laws of nature as it goes. Inside the bubble, particles would have different masses. Atoms might not hold together. The chemistry that makes life possible would cease to exist. Everything in its path would be destroyed or transformed beyond recognition.
This is called vacuum decay, and if it happens, there would be no warning. One moment, the universe is normal. The next, it is gone. The good news is that the universe has existed for nearly 14 billion years without this happening. Calculations suggest the false vacuum, if it exists, is very stable, but we cannot rule out the possibility completely. Vacuum decay is one of the most unsettling ideas in physics. It suggests that the universe we live in might be sitting on the edge of a cliff, stable only by chance, and we have no way to know when or if it will ever fall. We still don't know if time travel is possible. Time travel is a favorite idea in science fiction, but is it real? According to Einstein's general relativity, the answer is maybe. Relativity allows for paths through space-time that loop back on themselves, called closed time-like curves. In theory, if you could warp space-time enough, perhaps with a rotating black hole or exotic matter, you might travel into the past. But every time we find a potential method, problems appear. Traveling back in time creates paradoxes. The most famous is the grandfather paradox. If you go back and prevent your own birth, how could you have existed to travel in the first place? Some physicists think paradoxes mean time travel to the past is simply impossible. Others suggest the universe has a way of preventing them, perhaps through quantum mechanics or the way timelines branch. In the many worlds interpretation, changing the past might just create a new timeline, leaving the original intact. Time travel to the future is easier. If you move near the speed of light or sit close to a black hole, time slows down for you. When you return, years or centuries might have passed elsewhere. This has been tested and confirmed. But traveling backward stays uncertain. The laws of physics do not clearly forbid it, but they do not make it easy either. Whether time travel is possible or forever out of reach stays one of the most intriguing mysteries in science. No one knows if the past, present, and future all exist at the same time. We experience time as flowing. The past is gone, the future has not happened yet, and only the present is real. But physics does not support this view. In Einstein's relativity, space and time are woven together into a single fabric called space-time. Events do not happen in time, they exist at specific coordinates in space-time. From this perspective, past,
present, and future are all equally real, like different locations on a map. This is called the block universe. In this view, time does not flow. It simply is. Everything that has happened and everything that will happen already exists, laid out in four-dimensional space-time. If this is true, then the future is already there, waiting. You just have not reached it yet. Free will, choice, and change become harder to understand. Other physicists disagree. They think time is real and that only the present exists. The past is memory, the future is possibility. This feels more natural, but it is harder to fit into the equations of relativity. Whether time flows or whether all moments exist together is a question that sits at the edge of physics and philosophy, and we do not yet have a clear answer. Consciousness arises from the brain, but we don't understand how. You are aware. You experience sights, sounds, thoughts, and emotions. You have a sense of being someone, of existing. This is consciousness, and it is one of the deepest mysteries in all of science. We know that consciousness is connected to the brain. Damage to certain areas can change or erase aspects of awareness. Brain activity corresponds to mental states. Neurons firing in patterns seem to give rise to thoughts and feelings. But how? How does physical matter, cells, and chemicals produce the sensation of experience? Why does it feel like something to be you? This is called the hard problem of consciousness. Science can explain what the brain does, which regions are active, how signals move, but it cannot yet explain why those processes create subjective experience. Some think consciousness will eventually be explained by neuroscience once we understand the brain well enough. Others believe it points to something beyond physical processes, perhaps a fundamental feature of the universe itself. There are even ideas that consciousness might be connected to quantum mechanics, though these are controversial and unproven. For now, how the brain creates the mind, how matter becomes aware, stays one of the greatest unsolved puzzles at the intersection of biology, neuroscience, and philosophy. We still don't fully understand how life began on Earth. Life is everywhere on our planet. Bacteria in the soil, trees reaching for the sky, animals roaming the land. But how did it all start? How did non-living chemistry become living biology? We do not know. The earliest life appeared around 3.8 billion years ago, not long after Earth's surface cooled. But the steps from simple molecules to the first cell are still unclear. Scientists think life began with self-replicating molecules, perhaps RNA, which can both store information and catalyze reactions. In the right environment, maybe a warm pond or a deep-sea vent, these molecules could have organized themselves into more complex systems. But there are gaps. How did the first genetic code arise? How did cells form membranes to separate themselves from their surroundings? How did metabolism, the chemical processes that sustain life, get started? There is also the possibility that life did not start on Earth at all. Perhaps it came from space, carried by meteorites or comets. But that only moves the question elsewhere. The origin of life is one of the great unsolved mysteries. We know life exists, we know it had a beginning, but the path from chemistry to biology is still hidden in the deep past. We don't know if life exists anywhere else in the universe. The universe is vast. There are hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars have planets. Some of those planets are in the habitable zone, the right distance from their star for liquid water to exist. With numbers like that, it seems almost certain that life should exist elsewhere. And yet, we have no evidence. No signal, no artifact, no sign of biology beyond Earth. This is called the Fermi paradox, named for physicist Enrico Fermi, who asked, "Where is everybody?" If intelligent life is common, the galaxy should be full of civilizations. Some should be millions of years older than us. They should have spread across the stars, built structures we could see, or sent signals we could detect. But we see nothing.
There are many possible explanations. Maybe life is rare. Maybe intelligence is even rarer. Maybe civilizations destroy themselves before they can spread. Or perhaps space is so vast that we simply have not noticed them yet. Some think life might exist in forms we would not recognize, based on different chemistry, or living in environments we have not thought to search. Others wonder if we are truly alone, the only life in an empty cosmos. The question of whether life exists beyond Earth is one of the most important we can ask, and until we find an answer, we remain uncertain whether we are one among many or an isolated flicker of awareness in an otherwise silent universe. Aliens might exist, but we've never detected any sign of them. For decades, scientists have searched the skies for signals from other civilizations. Radio telescopes scan distant star systems. Probes search for signs of microbial life on Mars and the moons of Jupiter and Saturn. But so far, we have found nothing. The search for extraterrestrial intelligence, or SETI, listens for patterns in radio waves that might indicate technology. Thousands of stars have been surveyed. A few strange signals have been detected, but none have repeated or been confirmed. It is possible that intelligent life is out there, but not using radio. They might communicate in ways we have not imagined, or they might be so far away that their signals have not reached us yet. Light takes time to travel, and the universe is unimaginably large. Another possibility is that civilizations are deliberately staying quiet. If the galaxy is dangerous, making yourself known might be a risk. Or perhaps they have detected us and chosen not to respond. Some scientists think the absence of signals is itself a clue. It might mean that life rarely reaches the technological stage, or that it does not last long once it does. The silence of the cosmos is both humbling and haunting. We live in a universe that seems built for life, and yet we have never heard a single voice beyond our own. If aliens exist, we don't know why we haven't seen them yet. If intelligent life is common, some civilizations should be far older than ours. They might have had millions of years to explore the galaxy, build megastructures, or leave traces of their existence. Yet we see none of this. This is the heart of the Fermi paradox. One explanation is the Great Filter, a barrier that prevents life from becoming widespread. Perhaps the jump from simple chemistry to life is incredibly rare. Or maybe intelligence emerges often but self-destructs before spreading to the stars. Another idea is that advanced civilizations transcend physical existence, uploading themselves into virtual worlds or transforming into forms we cannot detect. If so, they might have no interest in exploration or expansion. It is also possible that interstellar travel is simply too difficult. Space is vast, and even traveling at near light speed, crossing the galaxy would take tens of thousands of years. Maybe no civilization has found it worth the effort. Or perhaps we are early.
Stars will keep forming for trillions of years. Most potentially habitable planets have not even formed yet. If so, humanity might be among the first intelligent species to arise. The absence of aliens is a mystery that touches on biology, physics, sociology, and chance. Until we find life elsewhere or confirm we are alone, the silence stays unexplained. We don't know how the first galaxies formed so quickly after the Big Bang. The James Webb Telescope has revealed something unexpected. Galaxies existed much earlier than we thought, some appearing only a few 100 million years after the Big Bang. This is puzzling because galaxies are enormous structures, and building them should take time. After the Big Bang, the universe was filled with hydrogen and helium gas. Over millions of years, gravity should have slowly pulled this gas together to form stars, which then grouped into galaxies. But the process should have been gradual. Instead, we are finding massive, well-formed galaxies at times when the universe was still very young. Some are larger and more organized than our models predict. This suggests that something in our understanding is incomplete. Perhaps dark matter clumped together faster than expected, speeding up galaxy formation. Or maybe the first stars were different from what we assumed, forming more quickly and in greater numbers. There is also the possibility that we are seeing only the brightest, most unusual galaxies from that time, while many smaller ones are still hidden from view. The early universe was a time of rapid change. How galaxies came together so quickly after the Big Bang is a mystery that challenges our models of cosmic history. Dark matter holds galaxies together, but we don't know what it's made of. We know dark matter exists because we can see its effects. Galaxies spin too fast. Clusters are held together by more gravity than visible matter can provide. The cosmic microwave background shows patterns that only make sense if dark matter is real. But what is it? Decades of searching have given us no clear answer. The leading candidate is a type of particle that barely interacts with ordinary matter. These are called WIMPs, weakly interacting massive particles. They would pass through normal atoms almost as if they were not there. Detectors buried deep underground have been waiting for a WIMP to collide with an atomic nucleus, but none have been confirmed. Another possibility is the axion, a much lighter particle predicted by some theories. Experiments are searching for them too, using powerful magnets and sensitive instruments. Some scientists think dark matter might be primordial black holes, formed in the moments after the Big Bang. Others suggest it could be something even stranger, particles that exist in hidden dimensions or interact only through gravity. Whatever it is, dark matter makes up most of the matter in the universe. It shaped the cosmic web, guided the formation of galaxies, and made the existence of stars and planets possible. Yet we have never directly detected a single particle of it. It is one of the greatest mysteries in all of physics. We don't know if dark matter is made of one type of particle or many. Most dark matter theories assume it is made of a single type of particle. But what if that is wrong? What if dark matter is a whole family of particles, a hidden sector of physics as rich and complex as the visible one? Some models suggest that dark matter might have its own forces, its own version of electromagnetism or nuclear interactions. If so, dark matter particles could clump together, form structures, or even radiate energy, all invisible to us. There could be dark atoms, dark molecules, even dark stars. These would exist alongside our universe but never interact with light, making them completely hidden from our telescopes.
If dark matter is complex, it would explain why we have not detected it yet. We might be looking for the wrong thing. Our experiments assume dark matter is simple, a single particle with specific properties. But if it is diverse, no single experiment would be enough. This idea is speculative, but it opens up new possibilities. A hidden cosmos might exist right next to ours, made of particles we cannot see or touch. Understanding dark matter may require not just finding one particle, but uncovering an entire new layer of reality. We don't know if dark energy is a constant force or if it changes over time. Dark energy makes up nearly 70% of the universe. It is the force driving the accelerated expansion of space, but we do not know if it is truly constant or if it changes. If dark energy is the cosmological constant, as Einstein once proposed, it has the same strength everywhere and always. It is a property of empty space itself, unchanging and eternal. But if dark energy is dynamic, something called quintessence, it could vary over time or from place to place. If so, the rate of expansion could speed up, slow down, or even reverse in the distant future. The difference matters enormously. A constant dark energy leads to one kind of universe, eternally expanding and eventually cold and empty. A changing dark energy could lead to entirely different fates, some more violent, others more surprising. So far, measurements suggest dark energy is constant, but the data is not precise enough to rule out small variations. Future telescopes and surveys will search for clues by watching how the universe's expansion changes over cosmic history. Dark energy is the dominant force shaping the cosmos. Yet whether it is a fixed feature or something that evolves stays unknown. And that uncertainty means the ultimate fate of the universe is still a mystery. The vacuum of space might not be empty but filled with invisible energy. When we think of empty space, we imagine nothingness. But according to quantum mechanics, the vacuum is anything but empty. It is filled with fields, flickering with virtual particles that pop into existence and disappear in an instant. These quantum fluctuations are not just theory, they have measurable effects. The Casimir effect, for example, shows that two metal plates placed close together in a vacuum will experience a tiny attractive force because of the energy between them. But here is the puzzle. When physicists try to calculate the total energy of empty space, the numbers come out wildly wrong. Quantum field theory predicts that the vacuum should have an enormous energy density, so large it would tear the universe apart. Yet measurements show that the vacuum energy, if it exists at all, is nearly zero. This mismatch is called the cosmological constant problem, and it's one of the worst predictions in all of physics. The calculated value and the observed value differ by more than 120 orders of magnitude. Some think dark energy is the vacuum energy, but even then the numbers do not match. Others believe there's a hidden mechanism that cancels out most of the vacuum energy, leaving only a tiny remainder. For now, the true nature of empty space, and whether it is truly empty, stays one of the deepest mysteries in physics. We don't know if space is continuous or made of tiny pieces. When you zoom in on a smooth surface, you eventually see grains, pixels, or atoms. But what about space itself? Is it smooth all the way down, or does it have a smallest unit, a fundamental grain? Some theories of quantum gravity suggest that space-time is not continuous but discrete, built from tiny units called Planck scale bits. At this scale, about 10 to the negative 35 meters, space might become grainy like the pixels on a screen. If space is quantized, it would change how we think about motion, distance, and even time. It could resolve some of the problems that arise when we try to combine quantum mechanics and general relativity. But we have no direct way to test this. The Planck scale is far smaller than anything we can probe with current technology. Even the most powerful particle colliders cannot reach those energies. Some scientists search for indirect signs. If space is grainy, light traveling across the universe might be affected in subtle ways. So far, no such effects have been found. Whether space is infinitely divisible or made of fundamental pieces is a question at the very edge of physics. The answer could reshape our understanding of reality itself. We don't know what came before the Big Bang or if the question even makes sense. The Big Bang marks the beginning of the universe as we know it, but what came before? Did anything exist, or is time itself a product of the Big Bang? If time began with the Big Bang, then asking what came before is like asking what is north of the North Pole. The question has no answer because there was no before. But some theories suggest the Big Bang was not the true beginning. In cyclic models, the universe goes through endless cycles of expansion and contraction. Each Big Bang is followed by a big crunch, which then triggers a new Big Bang. Other ideas propose that our universe budded off from a larger multiverse, or that it emerged from a quantum fluctuation in a pre-existing state. In these scenarios, something did come before, but it might be so different from our universe that our physics cannot describe it. We have no way of observing anything before the Big Bang. The event itself erased any evidence of what might have existed. All we can do is build models and look for clues in the structure of the universe today. The question of what, if anything, came before the Big Bang sits at the boundary of science and philosophy. It is one of the most profound mysteries we face. No one knows what most of the ocean floor looks like. We have detailed maps of the surface of Mars, the Moon, and even distant moons of Jupiter. But more than 80% of Earth's ocean floor has never been mapped in high resolution. We know more about the geography of other worlds than we do about the bottom of our own seas. The ocean is vast and deep, reaching down more than 11 kilometers in the Mariana Trench. Mapping it requires expensive sonar equipment, submersibles, and ships. Much of the seafloor has only been scanned at low resolution by satellites measuring the surface of the water.
What lies down there? We know there are underwater mountains, trenches, and volcanic vents. We have discovered strange ecosystems that thrive without sunlight, powered by chemicals from the Earth's interior. But vast regions remain unexplored. There could be unknown species, geological features, shipwrecks, and clues to Earth's history hidden in the deep. Some scientists believe the ocean floor holds answers about plate tectonics, climate change, and the origins of life. The ocean covers more than 70% of our planet, yet it stays largely unknown. Exploring it is one of the last great frontiers on Earth. Strange signals have been detected from deep space, but we don't know what they are. In 1977, a radio telescope in Ohio picked up a strong, narrow-band signal from space. It lasted 72 seconds and was so unusual that the astronomer on duty wrote "Wow" in the margin of the printout. The signal has never been detected again. Over the years, other mysterious signals have been found. Fast radio bursts, or FRBs, are intense flashes of radio waves that last only milliseconds. They come from distant galaxies, and for a long time, no one knew what caused them. Some have been traced to magnetars, highly magnetic neutron stars, but others remain unexplained. There are also repeating signals, regular pulses that seem too organized to be natural. When the first pulsar was discovered, astronomers briefly wondered if it was a message from an alien civilization. It turned out to be a spinning neutron star, but the question lingered. Most strange signals have natural explanations, but some do not fit neatly into any known category. Could any of them be artificial? Astronomers remain cautious, but the possibility is not ruled out. The universe is full of phenomena we do not yet understand.
Every strange signal is a mystery waiting to be solved, and each one carries the faint possibility that we might not be alone. We don't know why the universe appears so flat. When cosmologists measure the geometry of space, they find that the universe is remarkably flat. This means that parallel lines stay parallel and the angles of a triangle add up to 180 degrees, just like in the geometry we learn in school. But this flatness is puzzling. In the early universe, even the tiniest deviation from flatness would have been amplified over time. If the universe started out even slightly curved, it should be extremely curved by now. Yet it is almost perfectly flat. The leading explanation is inflation, a rapid expansion in the first fraction of a second after the Big Bang. Inflation would have stretched space so much that any initial curvature was smoothed out, like inflating a balloon until its surface looks flat. But inflation itself raises questions. What caused it? Why did it stop? And does the flatness of the universe point to deeper principles we have not yet discovered? The flatness of space is one of those features that seems too perfect to be an accident. Whether it is the result of inflation, fine-tuning, or something else entirely, it stays a mystery at the heart of cosmology. Cosmic rays strike Earth constantly, but we don't know where the most powerful ones come from. Every second, high-energy particles from space slam into Earth's atmosphere. Most are protons, traveling at nearly the speed of light. When they hit air molecules, they create showers of secondary particles that rain down on the surface. These are cosmic rays, and while we know they exist, their origins are still unclear. Lower energy cosmic rays likely come from supernova explosions, but the most energetic ones, with energies millions of times greater than anything we can create in a lab, are a mystery. What could accelerate particles to such incredible speeds? Supermassive black holes, colliding galaxies, and gamma-ray bursts are all candidates, but no single source has been confirmed. Even stranger, some ultra-high-energy cosmic rays seem to come from regions of the sky where there are no obvious sources. This has led to speculation about exotic phenomena, perhaps involving dark matter or unknown physics. Cosmic rays are a constant reminder that the universe is a violent, energetic place. But where the most powerful ones come from and how they are created remains one of the great unsolved puzzles in astrophysics. Lightning can strike upward from clouds into space, and we're not sure why. For a long time, pilots reported seeing strange flashes of light above thunderstorms. They described red glows, blue jets, and bright bursts that seemed to shoot upward into the sky. Scientists were skeptical. But in the 1990s, cameras finally captured proof. These phenomena are real. Red sprites are brief reddish flashes that appear high above storm clouds, reaching up toward the edge of space. Blue jets are narrow cones of light that shoot upward from the tops of clouds. Elves are expanding rings of light that spread across the upper atmosphere. All of these are related to lightning, but they happen at altitudes far above normal storms, sometimes reaching 90 kilometers up. They last only milliseconds, making them difficult to study. Scientists think they are caused by electrical discharges between the storm and the ionosphere, the charged layer of the atmosphere. But the exact mechanisms are still unclear. Why do they happen only during certain storms? What triggers them? These upward lightning phenomena were only recently confirmed. They remind us that even the atmosphere of our own planet holds mysteries. Earth is full of surprises, and the more we look, the more we find. Ball lightning has been reported for centuries, but we still don't know what it is. Witnesses describe glowing spheres that float through the air, sometimes passing through walls or windows. They hover, drift, and vanish without a trace. This is ball lightning, and it has been reported for centuries. The problem is that ball lightning is rare and unpredictable. Few scientists have ever seen it, and capturing it on camera is even harder. Most evidence comes from eyewitness accounts, which are not reliable. Some think ball lightning is a form of plasma, ionized gas held together by magnetic fields. Others suggest it could be a chemical reaction or even a type of hallucination caused by magnetic fields affecting the brain. There are dozens of competing theories, and none are proven. In recent years, a few videos and laboratory experiments have given new clues, but ball lightning stays elusive. Without consistent observations, it is hard to study. Is ball lightning real? Most scientists think so, but what it is, how it forms, and why it behaves the way it does are still mysteries. It is a rare reminder that not everything in nature has been explained. Some underwater sounds have no known source. The ocean is not silent. It hums with the sounds of waves, marine life, and shifting ice. But occasionally, hydrophones pick up sounds that do not match anything known. In 1997, an extremely loud, low-frequency sound was detected across the Pacific. It was named the bloop. For years, it was a mystery. Some speculated it was a massive, unknown sea creature. Eventually, scientists concluded it was likely the sound of ice breaking off a glacier.
But other sounds remain unexplained. The upsweep is a persistent noise that rises and falls in frequency. It has been heard for decades, but its source is unknown. It might be volcanic or geological, but no one is sure. Strange metallic noises, eerie hums, and other unexplained sounds are occasionally recorded. Most probably have natural explanations, but without more data, we cannot say for certain. The ocean is vast and poorly understood. Sounds travel far underwater, sometimes thousands of kilometers. What we hear might be geological, biological, or something else entirely. For now, the depths keep their secrets. Some ancient structures were built with techniques we can't fully explain. The Great Pyramid of Giza was built over 4,500 years ago. It is made of more than 2 million stone blocks, some weighing over 80 tons. These blocks were cut with incredible precision and assembled into a structure that remained the tallest building in the world for nearly 4,000 years. How did the ancient Egyptians do it? We have theories. Ramps, levers, and rollers are the most likely tools, but the exact methods stay unclear. No blueprints, no detailed records, just the pyramid itself. Similar mysteries exist elsewhere. Stonehenge, the stone spheres of Costa Rica, the moai of Easter Island, and the massive blocks of Pumapunku in Bolivia all raise questions. Some stones were moved across great distances. Others were carved with precision that seems advanced for the time. Most of these structures can be explained with known ancient technology, hard work, and clever engineering. But without written records, we are left guessing at the details. These monuments stand as reminders that ancient people were more capable than we sometimes assume. The methods they used might have been lost to time, but the results are still here, silent and enduring. We still don't know how ancient humans moved and placed the stones of Stonehenge. Stonehenge is one of the most famous monuments in the world. It stands on the plains of southern England, a circle of massive stones arranged with striking precision. Some of the stones weigh up to 25 tons. They were placed upright and capped with horizontal slabs, a feat that required careful planning and effort. How did the Neolithic people transport stones that heavy across such a distance? Some researchers think they were dragged on sledges, perhaps with the help of logs used as rollers. Others suggest they might have been floated part of the way on rafts. There are even theories involving glacial movement, though these are less widely accepted. Once at the site, the stones had to be raised into place. This likely involved wooden scaffolding, ropes, and ramps. The precision of the arrangement suggests careful measurement and planning. But no one knows for certain. Stonehenge was built around 5,000 years ago, long before written language existed in that region. The people who built it left no records. Only the stones remain, standing as a puzzle carved into the landscape. No one knows what caused the Tunguska event in 1908. On the morning of June 30th, 1908, a massive explosion occurred over a remote forest in Siberia. The blast flattened 2,000 square kilometers of trees, knocking them down in a radial pattern. The shockwave was felt hundreds of kilometers away. Witnesses reported seeing a bright fireball in the sky. But no crater was ever found. No large fragments of a meteorite were ever recovered. For decades, the Tunguska event was a mystery. The leading explanation is that a small asteroid or comet exploded in the air, perhaps 5 to 10 kilometers above the ground. The heat and pressure from the airburst would have been enough to flatten the forest without leaving a crater. But some details do not fit perfectly. Tiny metallic spheres and unusual particles have been found in the soil, but their origin is unclear. Some scientists think it was a comet, which would have been mostly of ice and left little evidence. Others argue for a stony asteroid. There are even more unusual theories involving natural gas explosions or black holes, though these are not widely supported. Whatever it was, the Tunguska event was one of the largest impact events in recorded history. And despite over 100 years of study, we still do not know exactly what hit the Earth that day. We don't know what causes certain animals to migrate such incredible distances. Every year, Arctic terns fly from the Arctic to the Antarctic and back, a round trip of over 70,000 kilometers. Monarch butterflies travel thousands of kilometers from Canada to Mexico. Sea turtles cross entire oceans to return to the beaches where they were born. How do they do it? Migration is one of the most remarkable behaviors in nature, but many of its mechanisms are still not fully understood. Some animals use the position of the sun or stars to navigate. Others sense the Earth's magnetic field, detecting subtle changes that guide them. Salmon are thought to use their sense of smell to find the rivers where they hatched. But many details are unclear. How do young birds, migrating for the first time without guidance from their parents, know where to go? How do animals navigate across open ocean with no landmarks? There is also the mystery of timing. How do animals know when to leave? Some respond to changes in daylight or temperature, but the internal clocks that trigger migration are not completely understood. Migration is driven by instinct, but the precision with which animals navigate over such vast distances suggests abilities we are only beginning to uncover. The natural world holds navigational secrets that science has not fully explained. Some birds and insects sense magnetic fields, but we don't know exactly how. Many animals can sense the Earth's magnetic field and use it to navigate. Birds, sea turtles, and even some insects have this ability. But how they do it remains one of the great mysteries of biology. In some animals, tiny crystals of magnetite, a magnetic mineral, have been found in their bodies. These could act like built-in compasses, responding to the Earth's magnetic field. But not all animals that sense magnetism have magnetite, so there must be other mechanisms. One leading theory involves quantum mechanics. Some birds may use a protein in their eyes called cryptochrome, which reacts to light and magnetic fields. When light hits the protein, it creates pairs of particles with entangled spins. The Earth's magnetic field influences these particles, and the bird's brain might interpret the resulting signals. If true, this would mean birds are using quantum processes to navigate, one of the few examples of quantum biology in action. But the details are still unclear. How does the brain read this information? How precise is the sense? Why do only some animals have it,